Hi, welcome back. If you skipped over the previous presentation, please go back and look at it at least once. Virtually everything I'm going to talk about in here assumes you at least have a conversational knowledge of the stuff I just talked about in the previous talk. And I don't want to retread too much of that material here just because we have space limitations. We can only burn so many CDs for this thing. I do want to go back and just summarize a couple of key points that are going to frame this talk. Remember we talked about we're building distributed applications, that's really what drives innovation and evolution in comm. And there are some key assumptions that are made by the architecture, and we have to acknowledge these and understand them. One assumption is that we want multi-user access to our application, that we have a lot of users sitting on the network. They're going to be issuing requests to our code to go get it to do stuff. And these requests will be sent over the network, either over the web or over a private network. And that somehow or another the user needs to see what we're doing and form these requests. So there's going to be some user interface GUI sitting on the client box that makes all of this happen. Might be a web browser, might be some custom application you write in VB or MFC or something like that. Whatever. We're not going to talk too much about how that part works because we don't do user interface in this talk. The second assumption is that we want distributed programming distributed across multiple machines. That is, we want to smear the load across several computers for a variety of reasons. It gives us the opportunity to do load balancing. It also allows us to better control over locality of reference in terms of where the data is versus where the code executes. It also allows us to get a lot greater concurrency and parallelism, right? A great way to scale is to add more hardware, right? And finally, because even Windows NT is known to crash from time to time, it gives us a certain degree of fault tolerance. That is, it allows us to recover, when one machine goes down, we can still at least have some semblance of order. Now, the third assumption is that bad things happen to good programs, and that eventually something really bad is going to happen, and the application is going to have an error, the system's going to crash, we get a blue screen of death. God only knows what's going to happen, and that when these things happen, the state of the application, that is the configuration state and the running state of the application, as much of it as possible needs to be able to be recovered, right? So that when we reboot the machines, we don't have to reinstall the operating system, which is something that is just a very unpleasant experience. Now, those are the assumptions. It turns out that also in this architecture that we live, this world that we live in, there are some guiding principles that direct how we write the code and how we build things. And the principles are pretty simple. They're on this slide. Principle number one is we put the application logic on server machines, not on client machines. And there's just a boatload of reasons to do this, having to do with locality of reference and resource sharing and a bunch of other things, which we talked about a little bit in the previous talk. In fact, that's really what the previous talk was about. The second principle says that transactions are the way we do things, that we have a programming model and it's based on transactional programming. And we're going to talk a lot about that in this talk. And transactions turn out to be at the core of so many parts of COM+ that we really need to spend a lot of time talking about that in this particular section. Principle 3 is that we build processes using COM. So we use COM for that first task that we talked about, which was component glue. But we let our components communicate using a variety of protocols and technologies, DCOM being but one of them. Turns out there's a lot of other protocols we can use that have a lot of benefits that make us not use DCOM as much as we might think we would to build a COM application. Now, the last talk really talked mostly about principle 1. That was how do we glue together the application logic into a server process that can work in a reasonable way, and that was all about context. This half of the talk is going to address principles 2 and 3, that is transactional programming and communications. Let's talk about what a transaction is. Transaction is a pretty simple concept. It's a unit of work presented to the system by a user. So a user has some will that they want something to happen. We're going to wrap their wishes inside of a little bag that we call a transaction. And we're going to make sure that all of their wishes that are carried out are protected by this transaction. And the reason we have transactions is to protect the state of the system. That is their role in our programming model. Now, to make this magic happen, we need something called a transaction manager, which is simply someone who coordinates the use and the outcome of that transaction. And the transaction manager we use in COM+ is something called the DTC, or Distributed Transaction Coordinator. And this is just a daemon that ships on every Windows 2000 box, and it's available freely in the option pack. So you can pretty much have it on any NT box that you want today. And the idea is my programs, my distributed programs, go off and talk to transactional resources. And they take the transaction that they get back from the DTC and they enlist the resource managers against this transaction, so that all of the changes they make inside of this transaction are protected, have the protection of a transaction, which is a very, very important thing to have, as we'll see. Now, I'm required by law to tell you about the ACID properties, but to be frank, I feel like violating the law today, and I'll defer you to one of the classic texts to go read about ACID transactions. What I want to do is focus on two of the four letters in ACID, that is atomicity and, more importantly, isolation. We say that a transaction is atomic, right? All the changes happen inside of a transaction at once, atomically. And in the case of a failure, it turns out that none of them happen atomically. That is, it's as if the transaction never happened. Right? And so at one level, we use transactions as an error recovery strategy, such that if we discover an error, we abort the transaction and all of the changes roll back, and the client either reissues the request or goes down an alternative code path. The second, and probably the more important aspect of transactions, is the isolation property. And the idea here is that the changes of one transaction are isolated from the changes of another transaction. And it turns out that we use transactions for concurrency control, that they're really a much more powerful and higher order concurrency control mechanism than the low-level stuff we get from the operating system, like the mutex or the semaphore. Right? Mutexes and semaphores are great for programming in the small, single process, single user, but lots of threads, just protecting a global variable. Hey, critical sections work great for that. But for programming in the large in terms of a runtime environment, it turns out that those things don't really scale well to having multiple processes or multiple machines. To do that kind of concurrent programming, we need to use transactions to protect all of our changes from the effects of other people. Now, a little bit of support goo needs to be explained here. As I mentioned, the DTC is a transaction manager. He's responsible for managing and coordinating the outcome of a transaction. Now, transactional programs talk to the DTC and say, please give me a transaction. And the DTC comes back with an object reference, a COM object reference. And the type of that reference is of type iTransaction. And iTransaction models what a transaction looks like. And it's got three methods, two of which are fairly obvious. One of them is called commit, which says, I'm done with this transaction, please commit all of my changes. The other, of course, is called abort, which says, I've changed my mind. These were a bad set of changes. I've detected an error. Please roll them back. The third method isn't really important. It's get transaction info. Allows me to get a bunch of various statistics. Now, the idea is the DTC allows transactional programs to begin transactions and acquire these iTransaction references, and then pass them to various resource managers to enlist the work of the resource manager against the transaction. And every resource manager I enlist on a single transaction, the work of those RMs composes atomically, right? Additionally, we're creating a set of locks. As I touch things inside of the scope of these transactions, I'm locking down everything I'm touching. And those locks are held for the duration of the transaction. So that if I make a change to, say, a database over here, that change is locked down and preserved for the duration of the transaction. So anything I saw or touched when I talk to the first resource manager, I can know is going to be maintained throughout the life of the transaction. It makes for a very, very sane programming model. Now, the way it's implemented, just a little bit of detail, is when I call commit on a transaction, so I go to the DTC, I get a transaction, and then I call commit. What happens is the DTC uses a protocol called the two-phase commit to coordinate the outcome of all of the resource managers that I've done any work with in that transaction. Now, it's a two-phase protocol that's very simple to understand. Phase one is often called the prepare phase. And at phase one, the DTC simply broadcasts to every resource manager, the user wants to commit. The user's happy, and we would like to roll forward. And at this point, the resource managers make sure that everything is good, and they save something onto disk so that in the case of a crash, they can come back and still roll forward. Phase two happens after all of the resource managers have acknowledged, or perhaps negatively acknowledged, the prepare. And at this point, we know the outcome of the transaction, right? We know we've either gotten consensus and everyone's happy, or at least one person dissented and we have an aborted transaction. And at this point, at phase two, the DTC simply broadcasts a second message to every resource manager saying, okay, you voted yes, here's how it turned out. And all of this stuff is just carried out in the plumbing. We never really see it as programmers. But because it's just such a part of the transactional vocabulary, we have to talk about it somewhere. And this seemed like a reasonable place to talk about it. So when you call commit, you're initiating the two-phase protocol. Phase one is prepare, where we're collecting votes and getting ready to roll forward. And phase two is where we actually finish the work. Now, let's try and bring this back to COM+, because the DTC, to be frank, has been around for years. You could have used it in the raw as a low-level C++ programmer, or even you can access it from VB if you're really deliberate and determined to do it. But in general, we don't touch the DTC very much. Rather, we want to do declarative programming. It makes a lot more sense to not have to write a lot of explicit code to go out and begin the transaction, manage it, do the enlistment. Rather, we want to get the runtime to do as much of this as we can. So here's the idea. As we saw in the previous talk, we declare our intent using attributes. I stick stuff on disk that says this component needs a blue, wet, and fuzzy runtime environment. And it's up to the COM+ infrastructure to make sure that when my methods execute, they execute in that kind of an environment. And of course, we call this environment what? A context, right? And that was the whole crux of the programming model from the previous discussion, right? That we use context to group together like-minded objects and to segregate objects that don't necessarily agree on what the world should look like. And that interceptors are used to map back and forth to call across these various contexts. Now, contexts turn out to be very, very critical to understanding how transactions and components can be mixed. Now, by default, when I drop a DLL into the COM+ Explorer, I've got nothing to do with transactions. So out of the box, I'm not going to be using transactions unless I go in and take a deliberate step to say, I'm writing code that's transaction aware. And this is a good thing, because as it turns out, transactions really influence the way we write the code more than you can imagine. Now, if I were to go into COM+ Explorer or some more exotic technique and set the transaction attribute to something as simple as transaction required, what happens is the runtime is very different now. My objects live inside of a DTC transaction, so that when the client calls co-create instance, my object lives in a context that has a DTC transaction, and we say that my object lives inside of the transaction, which is a very interesting use of vocabulary, right? While I live inside of a context, that's a kind of a normal way we think about COM programming, I actually live inside of a transaction, and because transactions are very short, it turns out my object is not going to live for very long either. We'll talk about the ramifications of this in a few minutes. Now, if I'm inside the transaction, I have control over the transaction outcome. And we'll see that through my context, I can influence whether the transaction can roll forward or not. Additionally, the context I'm running in will have a DTC transaction in it by the time my method needs one. So the client calls into me, I'm doing work, and as soon as I talk to an RM, there's going to be a DTC transaction stored in a well-known place in context, so that the resource manager can automatically enlist my work without me having to manually be touching iTransaction pointers, which is, to be frank, a bit of a nuisance because every resource manager has his own particular way of doing enlistment. The beauty of COM+ is that's a good thing. Let them all have their own private proprietary APIs for enlistment. As long as they know where to look, the declarative programming model will just tell them to enlist, and I don't have to worry about it. Now, there's an abstraction in transactional programming in COM+ that we need to frame really quickly here to make sure we all understand how this stuff works. And this concept is called a transaction stream. Now, a transaction stream is simply a collection of contexts within an activity. Now remember, an activity was a group of contexts in which there was no concurrent access. So typically an activity is a group of contexts and their objects that are owned by a particular client. Well, what we do is we subdivide the activity, which is just a group of contexts, into transaction streams. And we say that all of the objects within a single transaction stream will share a single DTC transaction. So that not only are we composing the work all of the RMs are doing against my method, all of the objects I create will compose with all of the RMs. And all of the RMs my child components use also will compose. So we kind of have this propagation story where the transaction stream begins typically at the first object the client creates. But then everything that object does, including talking to RMs or creating other transactional objects, we simply flow the transaction property downstream to all of these new entities. Now, the first context and object to be created in a stream, we call the root of the stream. And this guy has special significance in the model because he's the reason we have a transaction. Right? If it weren't for the root, we wouldn't have anything. So it's the existence of the root that mandates the fact that there's going to be a begin transaction call. But be aware, you as a programmer are never going to call begin transaction. Rather, it's going to be performed by the interception layer when we need to go off and get a DTC transaction. Now, the runtime will ensure that whenever you need one, if you look at this well-known place, which we'll see on the next slide or two, there's always going to be a transaction there. However, over time, there might be a different transaction because, as we'll see, the transaction runs until the root object is deactivated. So the client calls co-create instance, gets an object. That the transaction is basically triggered by the work of that object. When that object deactivates, it's now time to commit the transaction. So while there's no explicit begin trans or commit, it happens implicitly in the interception for you all the time. So begin trans happens because we have an object that's doing transactional work. Commit happens because the root object gets deactivated, which basically signals the root object is done. It's time to get out of here. Here are the attributes you can put into the catalog. And if you've done any MTS programming, you've seen all of these before. Right? This is very, very similar to the way MTS works. So the transaction attribute has 4 possible settings: not supported, supported, requires, or requires new. And this is a very, very similar table to the synchronization attribute that we looked at earlier on. Notice that based on this attribute, we can determine, will my object be in a transaction stream or not? Will I share the transaction stream of my creator? And the kind of interesting twist here is, will I be the root of a stream? And if I'm the root of a stream, that's important because it's my life cycle that's keeping the transaction open. So if I'm the root of a stream, it's imperative that my object go away as fast as possible because it's my existence that keeps the transaction running. Here's kind of a top-level picture of an object model in COM+. So notice that everybody lives in the same activity. So we can assume safely that some client created A created B, which created C, created D, and everyone's marked synchronization equals required. So all of these objects live in a single activity. That means there's no expected concurrency within them, by the way. Now, more importantly, inside the activity, we break it down into transaction streams. And notice that a given context and its object lives in exactly one transaction stream, or perhaps, as is the case with G and H, doesn't live in a transaction stream at all. Let's talk about the ramifications of this. A and B share a transaction stream. So what that means is they share a DTC transaction, so that the work of A will always be composed with the work of B. Either they both roll forward, or neither of them roll forward. G, on the other hand, doesn't have a transaction stream. All of his work against databases and queues and other resource managers won't have the protection of a transaction, which means it happens instantaneously and will never roll back. It's up to the component to somehow manually undo any work he does in the case of an error. So the error handling in A and B is going to be a lot simpler than the error handling in G or H. Another really interesting side effect of this model is A and B, because they live in the same transaction stream and same DTC transaction, share locks. So what this means is, if A were to go out and do, say, an update against a record in a database, okay, a lock is going to be acquired. And the way transactional programming works is locks are held until the end of the transaction. And this is the same way to build this stuff. So when A does the update, he acquires a write lock, which is an exclusive lock against some record or group of records in a database. If B were to go off and do another update against those records, or perhaps even a select statement, a read operation, there's no problem. And the reason for this is resource managers do lock management based on transactions, not based on threads or process IDs or anything like this. So that the work of A and B not only compose, but they share a lock space. So the locks that are held by A can be re-entered by B. And this makes it very difficult to deadlock just with those two components. Right? If, on the other hand, A holds a lock and then talks to G, G's not in a transaction. Right? G is in a totally different lock space from A. And if G were to try to re-enter the lock held by A, so if he tried to do a select against the table I had just done an update against in A while the transaction is still open, G's not going to be able to get back from the RM. G's going to deadlock. Right? G is going to basically be blocked until I release the lock. But because the lock is held for the duration of the transaction, we have a little problem here. Right? So one side effect of this model is we have to be very, very aware of how lock management works. Right? We can't just go turning on the transaction required bit, redeploying the components, and expecting everything to work. Right? If we have multiple transactions, or if we have non-transactional code mixed with transactional code, right? We have two different lock spaces, and we have the potential for deadlock, right? We'll see how MTS and COM+ deal with deadlock in a few minutes. Now, the transaction stream is a spatial relationship, right? It gets laid out at co-create instance time. It flows as normal context propagation at co-create instance time. However, within a given transaction stream, there's a transaction which is a transient phenomena. So as I make a method call into the transaction stream, a DTC transaction will be created, but that transaction will only live until the root object deactivates. When the root object deactivates, the transaction is over, but the stream remains in place, such that when I re-enter the object hierarchy, a new DTC transaction will be created. So again, this reinforces the fact that transaction streams are spatial relationships between contexts that just live out on the network, whereas transactions are transient or temporal phenomena that happen as we enter the object model and leave it. But over time, a given transaction stream will see chained transactions. Here's a picture that I hope drives this point home. Let's assume that this is a simple object model where the client goes off, some VB form or what have you, goes off and creates A through co-create instance, and A creates B, which then creates C, which then creates D. Okay, let's talk about how this scenario gets glued together. Let's assume A is marked transaction required. If he's marked transaction required, we also know he's marked synchronization required because transactional objects have to have an activity. So not only will we get an interceptor created and an object instance, we'll also get an object context because that's how this plumbing works. Because we were marked synchronization required, that green reference will point to some valid activity data structure. Because we're marked transaction required, that black reference will refer to some valid transaction stream data structure. And if we dig into the transaction stream, don't have to dig very far as it turns out, there's an iTransaction object reference which will point to a valid DTC transaction so that when my component needs to enlist, we can just reach into the context through a well-known device and grab that iTransaction star and do stuff with it. So can the resource manager. Now let's assume that A created B and B is marked transaction requires. What this means is, just like with the activity, we present the properties of the creator and they flow downstream to the new context. And because he was marked transaction required, he said, I am willing to allow the transaction property to flow so that my transaction stream flows through to B. So that A and B see the exact same DTC transaction and their work composes and they can share locks, right? Very, very nice. Let's say that B creates C, but C is marked transaction not supported. Well, in this case, while the activity can flow, notice the green reference still points to that big giant green activity. The black reference, which is the transaction stream, points to a null, it's a null reference. Which means if C goes off to do data access or anything else with a resource manager, there will be no enlistment. Right? There's no transaction to protect C's work. If C creates D and D is, let's say, marked transaction required, note that we stopped propagation. We only propagate object context one hop at a time. And because C doesn't have a transaction stream, D gets a brand new transaction stream, which also implies a new DTC transaction. This means that while D's work will be protected by a transaction, it won't compose with A and B. That means that A and D, for example, can't share locks, right? We're going to have a problem there. Also, the outcome of the two transactions is in no way coordinated. A's transaction can commit, B's can abort, B's can commit, A's can abort. All four combinations are possible, right? There's no attempt to coordinate the outcome of these transactions. Now, as that previous picture showed you, if I'm in a transactional component, there's an iTransaction object reference stored in a well-known place. Now, this well-known place is consulted by two entities. The resource managers I talk to know the well-known place. And if I talk to them through approved mechanisms, like ODBC or OLADB in the case of databases, or just using the MSMQ API, these RMs know to look in the well-known place. And if I ask a database or a queue to do work on my behalf, if I have a transaction, he'll automatically enlist. I have to write zero code to take advantage of this. Right? Simply by saying transaction required, all of my data access and all of my message queuing and any other resource manager work I'm doing now automatically will enlist on the transaction. Occasionally it's useful to do manual enlistment, and there are some very, very esoteric cases which are outside the scope of this talk. In these cases, the well-known place is exposed to me in COM+ through the iObjectContextInfo interface. So if I need to get my iTransaction reference for any reason whatsoever, I can simply reach down, do a get object, co-get object context, get the iObject context info pointer, and call it get transaction, which returns to me the iTransaction reference, which I can then do manual enlistment against, or maybe some various esoteric bookkeeping that I might want to do, like finding out statistics about it. Now, if you've done any MTS work, this slide's going to be somewhat interesting because COM+ changes the point of acquisition a little bit. Let me explain what I mean. The transaction will be acquired or initiated by the runtime when it's needed. Right? Now, in MTS, we had a very, very simple model. In MTS, the transaction was initiated the first time we made a method call into the transaction stream. So even if you weren't going to talk to any resource managers for 5 more method calls, we acquired the transaction at the first call automatically. Right? Very simple implementation, and it basically worked fine. COM+ is a little bit smarter. What COM+ does is if you're a transactional object, we don't technically get a transaction for you until someone looks in the well-known place. That is, if I talk to a resource manager and he attempts to auto-enlist, it's at that moment the begin transaction will happen down in the runtime. Or if I'm doing manual enlistment, if I reach down and do a get transaction against my context, that too is going to trigger a begin transaction call. Now, the transactions are created with a timeout. And the timeout defaults to 60 seconds, but it's configurable on a machine-by-machine basis. 60 seconds, to be frank, is way too long. Right? We want the transaction timeout to be as short as possible because the transaction timeout is the way we detect and break deadlocks. And the shorter the transaction timeout, the sooner we can detect and break a deadlock, which allows us to get the throughput of the system back up. Now, that's when the transaction begins. The transaction will be ended, or we'll try to commit the transaction, again, when the root object deactivates. That bullet appears on about 8 slides in this talk, and I can't say it enough times. The transaction commits when the root object deactivates. Right? That's the way the programming model works. We began the transaction because the root object existed, and we end the transaction when the root object goes away. And this can either mean the client releases his proxy, or hopefully the root object sets his done bit from JIT activation to deactivate the object at the end of the method call, which will trigger the end of the transaction as well at the end of the method call. And this is really the way we want to program. If I'm running inside of a transaction as a COM+ component, I'm kind of like a resource manager. Right? Remember I mentioned the 2-phase commit protocol. Phase 1 was prepare, where we do vote collection and preparation. Phase 2 was notification. And as it turns out, a transactional context is kind of like a mini resource manager. And here's what I mean. Every transactional context keeps a property called the happy bit. And the happy bit is set to true when the transaction begins. However, my method call, as part of his work, can determine we are either temporarily or permanently unhappy. That is, we're unhappy with the results of this transaction. And we can set or clear this happy bit programmatically through our object context. Now, at prepare time, what happens is the DTC and the enlistment plumbing goes through and looks at all of the contexts and consults the happy bits. And if and only if all of the contexts are happy, we can roll the transaction forward. If at least one context is unhappy, that is, if I've cleared my happy bit, transaction's going to abort, and not only will my own work be rolled back, but everyone else in the transaction stream's work will be rolled back. And it will be as if none of this stuff ever happened. There's an interesting synergy between the 2 bits that we've talked about so far in these talks. The happy bit is there because we're a transactional component. And there's another bit, which we talked about in the previous discussion briefly, called the done bit. And this was there for JIT activation. Now, if I set the done bit and return control to the interceptor, my object will be deactivated, it will be pulled out of the context. And what I'm saying if I'm transactional is, I have no more meaningful work to do inside of this transaction. Now, think about what that means. If I set the done bit to true, that is, I say, I am done, but I clear the happy bit, I indicate that I'm unhappy. What I'm saying to the system is, I'm not happy, but I'm done. Which means this transaction is screwed. This transaction is fouled up, and there's no way I can fix it because I'm done. When we do this, we say that we trigger the dooming of the transaction. And what this means is the transaction stream keeps a doomed bit, which records the fact that someone left in this terrible state of being done but unhappy. And this makes sure that the transaction can never commit and the transaction will definitely be doomed no matter what happens. Here's a picture of all these bits and trying to sort it all out. Notice that each context has a happy bit and a done bit. And the default state, by the way, is I'm happy, but I'm not done. Also notice that every transaction stream keeps a doomed bit. And the doomed bit says, is this transaction doomed? And of course, notice the default there is that it's false. Right? I use my object context interfaces to change the happy and done bits. Right? And based on the state of the happy and done bits, if I leave in done and not happy, that will latch the doomed bit for the duration of that transaction, ensuring that the transaction gets aborted. Right? And it's basically, that's the closest we get to an abort call in the COM+ programming model. Now, if you're an MTS programmer, there was an interface that you used called iObjectContext. And this was kind of the grab bag of all methods in all of MTS. And this interface has been refactored in COM+, and while it's still supported, it's being replaced or augmented with a better set of interfaces that are better factored and much more targeted to the task at hand. Unfortunately, the interface that's used to set the happy and done bits hasn't been documented yet, so I feel rather uncomfortable using its name out loud for fear that it will change radically by the time you see this. So this slide really shows you the old MTS interface. And iObjectContext had 4 methods: set complete, enable commit, set abort, and disable commit. This table shows you what it did to the happy and done bits. And the semantics of those method calls is indicated in the column on the right. And notice that set complete said I'm happy and I'm done. I'm happy with the state of the transaction and I have no more work to do. And what that really means is commit. This is the closest we get to a commit call in the COM+ programming model. And what it really means is commit if and only if I'm the root. If I'm not the root, we deactivate the object, but really to no end, right? Because remember, it's the root object's life cycle that determines when we trigger the commit. Set abort says I'm not happy, but I'm done. And this says abort this transaction. And it, in an almost synchronous way, aborts the DTC transaction underneath you. Disable commit's an interesting state. Disable commit says abort the transaction unless I get another method call, because notice the done bit isn't set. Disable commit says, if you were to try to commit after I return, we have a problem because I'm not happy. But I'm also not done. If you call me again, I can go set complete, in which case life is going to be great. Enable commit really exists for completeness, and in mainstream COM+ and MTS programming, it's just not used that much. Right? The real bread and butter states are set complete, set abort, and to a somewhat lesser degree, disable commit. Oh, this one. If I throw something at the camera and we lose video, I apologize. There's a lot of confusion over how the programming model works, and I'm going to try and keep my temper under control as I explain it to you. I get really passionate about this topic because a lot of people misconstrue the semantics of how COM+ works, so I'm going to try and keep it together, but if I go ballistic, I really apologize. I'm going to take a deep breath. Remember, transactional objects live inside of a transaction. And the idea is, when the transaction ends, the transaction is over, and everything that happened in the transaction is done. Now, what this really means is, the objects that lived in the transaction stream are considered stale. What happens is, at the end of the transaction, no matter what state of your happy and done bits you were in, at the end of the transaction, the COM+ runtime is going to take all of your objects up against the wall and kill them. It's going to deactivate each and every one of them. This means every transactional object must support JIT activation, and this is enforced by the catalog manager. And the reason we do this is to enforce transaction isolation. And here's the simple reason. Remember that we hold locks for the duration of the transaction, but no longer. If a component were to read something inside of a transaction that was the result of another component in the same transaction, the results of that work are held constant for the duration of the transaction. However, once the transaction commits or, God forbid, aborts, all of the locks have been released. And any cached information you would have read in the first transaction is now subject to change. And so to simplify the programming model, we deactivate every object in the stream when the transaction is over to ensure that no residue from previous transactions infects future transactions, violating transaction isolations. So this is really about ACID properties, and this is why we deactivate objects all of the time in the COM+ programming model. There is no way to keep state across transaction boundaries in a transactional object. If you want to do it, A, be aware of the isolation problems that you can be causing. And B, you have to do it by having a second non-transactional object that lives for the duration of the communication session of the client, right? And this is how it's done. An interesting innovation that came out in COM+ is something called Bring Your Own Transaction, or BYOT. And what BYOT says is, I like declarative transactions, but occasionally I have to go to the DTC myself or some other transaction manager and acquire a transaction. And I'd like to be able to have a manually controlled transaction that I can control the timeout, the isolation level, and when commit and abort get called. Yet I'd still like to enlist transactional components onto that DTC or other transaction. And so BYOT was added to allow us to do this. And so the idea behind BYOT is I go off to the DTC, get a transaction, and then use this interface and co-class that are shown on this slide to basically say, create this other transactional object with this as the root of the stream. So notice the first parameter to create is an iTransaction reference, which says, I'm holding a transaction already. Please enlist this COM component and everything he creates against this DTC transaction, right? And BYOT is largely useful for fine-tuning timeouts as well as controlling isolation level on a per transaction basis. There's an implied model from all this. I mean, I feel like I've just dumped a lot of heavy concept stuff on you and haven't given you enough solid, concrete implementation stuff to talk about. Let's talk about the model that's implied by all of this. Right? It's very, very simple. Right? Any work we do against resource managers, like databases and queues, is going to be protected by a transaction. And this happens via the auto-enlistment plumbing and our context. Also, any objects my object creates, because of context propagation, are also going to auto-enlist against the same DTC transaction. So we're basically composing a bunch of work out on the network inside a single transaction. Every method in a transactional object is encouraged to call setComplete, to go setComplete, simply to keep the transaction time as short as possible. And we do this because the shorter the transaction, the higher the throughput, because we're holding locks for a shorter period of time. This is the key to scalability. Now, we keep the important state of our application under resource manager control, which for the most part means we're putting our application state in databases. We do this because we want the protection of a transaction. We want to be able to recover in the case of a power outage or application error. The only state we really keep in our objects in a COM+ application is session state, stuff that isn't expected to survive a crash. It's not going to be shared by multiple users, and it's not going to be protected by a transaction. And this is very, very different from classic object orientation. It's also very, very different from the way, say, Corba works, which is a distributed object technology you may have heard about. Right? Corba is a very, very simplistic worldview where it's just object RPC. COM+ says no. Objects are great for programming in the small, but distributed programming needs these deliberate acts which are basically based on transactions. It's just a very, very different model than you might be used to. A lot of people talk about connection pooling when they talk about COM+ and MTS. Let me say a few words about that very quickly. COM+ and MTS provide resource pooling, and COM+ adds object pooling for expensive resources, things like database connections, certain classes of pooled objects. Right? There's pool management code built into the COM+ infrastructure. And the way it works is COM+ maintains a pool per transaction. And the reason we do this is because enlistment turns out to be expensive in many situations. So we not only want to amortize the connection establishment cost, which can be very expensive, we also want to amortize the cost to enlist the resource on a particular transaction. So we maintain pools on a per transaction basis. Now, components are encouraged, if they know they're using pooled resources, to acquire the pooled resource at the last possible moment. This means the moment before you want to send the SQL down to the database, that's the time to acquire the connection. Don't do it in your language level constructor. Don't even do it in iObject control activate. That's too early. Acquire the connection at the very last moment. Use it, and then as soon as possible, as soon as that statement completes, you want to tear down the connection. You want to release the connection, which in fact doesn't tear down the connection, but rather just puts it back into a free list so some other component can get access to it. Right? A big key to scalability is acquire these resources at the last possible moment and release them at the first possible moment. if you find yourself wanting to put database connections as data members in your classes, stop, slap your hand, hit the backspace key, and write the code the way I just described instead, right? Putting database connections as data members in a component is a bad idea. Yes, I know JIT activation will help a little bit, but it doesn't help nearly enough, right? The model is acquire at the last moment, release at the first possible moment. Something happens when we use transactional resource managers. Our programs sometimes get slower, right? Because often we're keeping the state in another process, like a SQL Server process or something more exotic. And occasionally I'd like to keep the stuff I read from a transaction up here so that I can continue to work with it without having to go back to the resource manager inside of every transaction to go back and reread that information. And it turns out that to build a cache that doesn't violate transaction isolation properties is very, very difficult without a lot of support goo, right? Just putting stuff in a global variable or in a piece of memory or something isn't going to be enough because we need to coordinate our cache with the outcome of the transactions as well as deal with the lock management. So prior to COM+, it was really, really, really difficult, if not almost impossible, to build a transaction correct cache. Fortunately, the COM+ release of the DTC has some innovations that make it possible to build transaction-aware caches. And in fact, there's a transaction-aware cache that ships with COM+ called the In-Memory Database, or IMDB. And what IMDB is it's an OLEDB provider, which means it's like an ODBC driver, right? It allows me to talk to data, right? IMDB is an OLEDB provider that makes memory look like a table. Now, the things that IMDB offers to me is first, it's transaction aware. So IMDB is completely happy to enlist on my declarative or manually managed transactions. And it supports the transactional concurrency model, so all of the locks are handled in the correct way. Additionally, the IMDB cache will roll back based on the transaction outcome. So if IMDB caches something and the transaction aborts, it reverts back to the previous state. Right? Very, very important if I'm going to build a transaction-aware cache. Some other interesting aspects of IMDB is the cache memory is stored in a shared memory section. So it's visible to all processes on that host machine. So if I have several server applications that are caching information from a common table in a database, for instance, we don't have to replicate that memory from process to process. We just keep it in a single piece of virtual memory, and we let the virtual memory manager deal with cache coherency amongst all of the processes on this machine. Now, another interesting tidbit is the IMDB data provider is implemented as a configured pooled component. You can actually go into COM+ Explorer, look at its attributes, see how it's configured, and it's got some interesting aspects if you go and look at it. Now, there are two common usages of IMDB, or two common scenarios in which we use IMDB. One of them is as a somewhat smart cache against an OLEDB data source, more often than not a database system, but it could be any OLEDB provider. The other use of IMDB is as simply transactional shared memory, right, where we're not actually caching a back-end data source, but rather all we're doing is having a transactional piece of shared memory that everybody sees and we can enlist against our transactions. Now, when we're using it in the role of a cache, it turns out that we need to declaratively control which data providers and which catalogs and which tables this IMDB data source is going to act as a cache against. So the COM+ Explorer has a fairly rich user interface for configuring a bunch of named configurations of IMDB that correspond to a variety of OLEDB data providers and their underlying tables. So here's kind of the model. You know, your components, the programmer, you're the guy at the top, programs against IMDB. And sometimes IMDB is acting as a transactional cache against back-end data sources, like in the first two cases there. Other times we use a null data provider, if you will, called @IMDBTemp, which says there is no back-end provider. We're not caching anything. This is the entire representation. But I want it to be transactional, and I want it to be in shared memory. Here's a little bit of code. This assumes, of course, that you've got the COM+ Explorer bits already set up, and that you've set up some sort of a data provider. And I'm assuming here that you've configured an IMDB configuration called SQL pubs, and that you're caching the table called authors. Now, here's the ADO code in Visual Basic that's needed to access that table through IMDB. So notice that we set up an ADO connection just like we would for any other data access. But we set the provider property to MS-IMDb. This says don't use ODBC, don't use the OLEDB native provider for SQL Server or what have you, but rather load the IMDb provider, which is this transactional cache. We use the connection string attribute to control which of the configurations we've set up in COM+ Explorer we want to use for this particular application. In this case, we're assuming we've set up a configuration called SQL pubs, and that's the thing I've set up in COM+ Explorer. Interestingly, I set the cursor location to AD use none. The last thing we want is another cursor library and another layer of memory access between the IMDb cache and my code. So we set the cursor location to AD use none to bypass the client cursor library or any other goo that ADO and friends might want to layer between me and IMDb. And then we issue the open call. Okay, so at this point, we've got an IMDb data provider open, we're holding references to it, we're ready to start accessing tables. And so to do that, we, of course, create everybody's favorite object known to man, the ADO record set. And we do a record set.open, giving it not a select statement. Notice this is not a SQL statement, but rather just the raw name of the table as we've configured it in COM+ Explorer. And typically it correlates exactly with one-to-one relation to the tables out in your databases, but it doesn't technically have to. So we'll assume we've configured that we want a table called authors, which of course naturally would be a cache against the authors table in the pubs database of SQL Server. And of course we give it the connection reference as the second parameter. And away we go. All access now through this record set is going to go through the IMDb cache. And reads are not necessarily going to generate data access. In fact, they aren't going to generate data access. We'll talk in a few minutes about how our updates translate down to the database. What you might have seen on that previous slide, and I almost discussed it then, but I thought I'd wait till this slide, is that IMDb doesn't support SQL. That is, it's a very simple OLEDB provider that supports the data source object, it supports sessions, it supports tables and row sets, but it doesn't support commands. So you can't really create an ADO command object and expect it to work like it would against SQL Server. You can't say select star from this, where that. None of that stuff works. There's no joining. It's basically just raw tabular access to tabular data. If you want sorting and filtering, you get this through the way ADO does it, right? You're going to basically leverage all of the ADO sorting and filtering capability. It's not going to be done by the underlying infrastructure, and you're not going to be able to get it by doing sort clauses or group by clauses in your SQL. To make all of this magic work, we have to have some sort of an index to go with every column that we decide to sort against. Additionally, if I'm going to go off and build my own tables using @IMDbTemp, I have to make sure that if I want to support sorting, that I set up the appropriate indices to enable sorting against an IMDb table. Now, the scenario we just looked at in the previous example used IMDb as a transactional cache in front of a SQL Server or equivalent database. The other application, of course, is to use IMDb simply as a transactional piece of shared memory. And to do this, instead of saying, setting the connection string to something like SQL pubs, which is what it was on the previous example, we set it to @IMDbTemp, which is a signal to IMDb that there is no backend database to cache against. There's no memory to go out and read. We're basically going to go off and define a bunch of new tables that have not existed before ever in the world. So to do this, we have to use some sort of a DDL mechanism. And if we're low-level OLEDB programmers, we use ITable definition and INdex definition. If I'm a VB programmer, I'm going to use the ADOX extensions from OLEDB 2.1, which of course install with SQL Server or anything new. Of course, Windows 2000 ships with these as well. But the bottom line is, if I use @IMDbTemp, it's up to me now to define the schema at runtime, because I can't really do it declaratively, using these programmatic interfaces, either ADOX or ITable definition if I'm a low-level OLEDB person. So here's an interesting little bit of code here. If you look at the code at the top, what it's doing is it's going off and saying, I want to use ADO with the MS-IMDb data provider. But rather than having one of those configured caches like we used in the previous example, we simply say the connection string is @IMDbTemp, which means I'm going to go off and define some tables myself. I then open the data source by saying con.open, and away we go. So we've got an open source, we've got an open reference to a data source with no tables in it. If you look at the second code fragment down towards the bottom, right, what we're doing here is we're using the ADO extensions that are part of OLEDB 2.1 or greater, and saying, okay, great, I've got a new table and I've got a catalog. we go off and we create a new table object. We give it a name, in this case, my table, right? And we append elements to the columns collection of the table, saying I want to have a column called ID of type integer. I want to have a column called name of type varchar, and its maximum length will be 100. Right? So I basically set up my schema through this table object. I then associate the catalog object with the IMDb provider, and I say, okay, catalog, here's my table, append it to the schema. And through this sequence of code, I've done the moral equivalent of a create table statement in SQL. Right? And basically just set up a new table, which I can now then go off and program against, which is what we see on this slide. Right? This slide assumes the previous code has already run. And in this case, we go off, open up the record set called myTable, open up the table called myTable, which was the schema we just defined. And in this case, we go off, create some fields, create some values, set them up with the columns and values, and away we go. Right? We put them into the record set by doing a record set.addNew, and this basically just adds an element to the shared memory table. It's transactional. If my transaction aborts, that entry goes away. And it's cache coherent on this machine, which means all other processes will see that change as soon as the transaction commits. Right? The code on the right-hand side of the slide just shows the traversal code, which is it's very vanilla B-flat ADO code. There's really nothing to say. Right? We open the table and walk through it. Right? The main note is on the previous slide, we had to define the schema programmatically at runtime. And that's really the interesting thing about using add_IMDb_temp. So how does it all work? Well, there's really two pieces of IMDb that we wind up interacting with. The IMDb core runs as a daemon inside of an NT service called imdbserve.exe. And this thing either starts up as an NT service at boot time, which is the default, or if we're having problems with security or what have you, we can start up from the console to get diagnostic messages. And the IMDb core is just running on our machine. However, most of the time, we're simply using the IMDb proxy, which is the provider, which, if we're only doing read operations, is all we need. Because the proxy sees the shared memory that's in the cache, is able to touch it, reach out, grab it, fine. We don't need to take a process switch if all we're doing is reads. If, however, we're doing writes, the writes go through the IMDb core. Right? And what happens is we have to deal with the fact that what if we're a cache? Right? What if I'm making changes to the cache? Those changes have to be written through, they have to be written back out to the back-end table. Right? And so what happens is there was an extension put into DTC called phase 0 notifications. And the IMDb core registers for phase 0 notifications and says, aha, the client just tried to commit the transaction. I see that you've made a change to the cache. Before we start the normal two-phase protocol dance, I will go ahead, enlist a connection to the database, and shove the changes down the OLEDB pipeline, right? And enlist the back-end RM. At that point, we not only have the cache enlisted for the two-phase commit, we have the back-end data source enlisted. Right? And so this is how we're able to keep coherency between the back-end data source and the transactional cache. Now, this just happens. We don't have to do anything, but just be aware that reads against IMDb are really, really efficient. Writes to IMDb require a write-through every time we do the write. At the end, the good news is, however, we do it at the end of the transaction. One last note, to make IMDb programming even easier, there's something called the Transactional Shared Property Manager, which works very similar to the Shared Property Manager of MTS, that's implemented using IMDb that basically gives us a programming model that looks very similar to the old Shared Property Manager, but it gives us transaction enlistment. It also gives us the scope of the machine instead of the scope of the process in terms of sharing. So that's IMDb. There's one more piece of transactional plumbing I want to talk about before we move on, and this is something called compensators. Recall that a transactional object lives inside the scope of a DTC transaction. That is, your object is scoped more or less between the begin trans and the commit. Now, we can influence the outcome of the transaction simply by setting or clearing the happy bit. Right? And that's a reasonable way to ensure that the transaction doesn't commit without us being happy about things. However, prior to Windows 2000, there was no simple way, at least, for our object to directly participate in the two-phase commit. That is, for example, there was no way for our transactional object to ever find out the outcome of the transaction. Think about it. We lived inside the transaction. By the time the transaction outcome is known, we're gone. Right? Our code is no longer around to now handle the outcome of the transaction. Fortunately, we have some new plumbing now in COM+ that allows us to do that kind of thing. And this plumbing is called generically the Compensating Resource Manager. And the Compensating Resource Manager is plumbing, it's infrastructure, that allows transactional objects to specify a second class ID and component that will represent it during the two-phase commit. There's still no way a transactional object can live beyond the scope of the transaction. However, we can designate a second component to represent us at the two-phase commit. This second component is called a compensator. And the reason we might want to use compensators is to provide transactional protection around otherwise unprotected operations, like file access. I delete a file. Maybe I would like to put the file back if the transaction aborts. My component can't do it because I don't know the outcome. My compensator can. Anytime I do an unprotected operation, I'm at risk of violating the semantics of my application unless I protect those operations or unless I'm very aware of it. So compensators allow me to basically, it's the poor man's resource manager. It allows me to get a lot of the benefits of having transactional resources without having to program against the low-level DTC interfaces. And as we'll see on the next couple of slides, compensators exist at the outer edge of the transaction. That is, they exist only within the two-phase commit protocol. That is, they aren't created until the commit is initiated, and once the two-phase commit protocol is over, the compensators are gone. And here's the picture, right? Horizontal axis is time. Begin trans happens. Some transactional objects do their work inside the transaction. Root object deactivates, which triggers the commit. And it's at that point that the compensators that have been registered inside the transaction get created and get to do work both in the prepare phase and in the notify phase of the two-phase commit. Once the DTC has been ACKed or acknowledged for all of the notifications, compensators are all gone and none of these guys exist. Now, let's take a quick look at how this stuff works. The compensators are just components. They're just components you can write in Visual Basic, Java, C++, whatever your programming language choice is this year, right? You can write a compensator in that language. And the compensator implements a very simplified version of what the DTC expects from a resource manager. Now, the compensator will be asked by the system to do a prepare at phase one, which means your compensator, A, gets to be notified that the transaction is about to be committed, and B, it gets to vote no. It can say, no, there's no way I can possibly prepare. We're in really bad shape. Tank this transaction. Additionally, once the outcome of the transaction is known, that is, at the end of phase one, we know the outcome, during the notification phase, which is phase two, your compensator will then be notified, okay, you voted yes, so did everyone else. We're committing. Or you voted yes, but somebody else voted no, we're aborting the transaction. And it's at this point your compensator can do the most interesting part of its work, which is either to initiate a compensating transaction to undo something you did inside the transaction earlier, or perhaps to clean up any resources that you acquired along the way. Now, to make all of this stuff happen, the plumbing, the infrastructure, manages a log on your behalf to store state between all of these phases. Because it turns out that to be a real resource manager, we have to be able to survive crashes that happen after phase one but before phase two. Because if I said prepare yes and everyone else does, we still have to make the transaction happen. So all the log management is handled by the system, and we have a very, very simplified interface to the log that allows us to read and write records in a very, very simplistic way. So the idea is my transactional object registers the fact he needs compensation and writes out one or more log records using the system's log manager to basically send information downstream to the compensator. It's kind of like a deferred procedure call, if you will. When the transaction commits, we then enter phase one, and at phase one, we're at prepare time. Your compensator will be created, and all of the log records you wrote out inside of the transaction get delivered to the compensator. So this is basically your way of doing a deferred procedure call against the compensator. Compensator gets a chance to vote. He also gets a chance to either let those records from inside the transaction stick around in the log for phase two, or drop them, or even write new records for later use at phase two, and he gets to vote. So we do all of these things in prepare phase. At the end of the prepare phase, we know the outcome of the transaction, and at this point we're in phase two, or the notification phase. The compensator will then be delivered all of the records that remained in the log, either the old ones or the new ones we put in at prepare time. These things will then be delivered to the compensator, at which point he does whatever he needs to do to compensate. If it's a successful transaction, the odds are there's not a lot to do. If it's an aborted transaction, the odds are we're going to issue a compensating transaction to undo the work we were trying to protect back inside the transaction. Now, to use compensating resource managers, your object and the compensator have to be configured to run in an out-of-process or server application, and the Enable Compensating Resource Managers checkbox needs to be turned on. This is what triggers all of the recovery code that looks at the transaction log when the process restarts and runs all of the phase 2 cleanup code. Your compensator is a non-transactional component that's expected to implement the interface ICRM compensator or ICRM compensator variants. We'll see both of those interfaces. You implement one or the other. Now, the object and the compensator communicate with the log via this third component that's provided by the system called the clerk. The clerk implements an interface called ICRM log control. And ICRM log control allows the transactional object to indicate who his compensator is. It allows anyone to write log records to the log, and it provides a few other low-level services for controlling write-throughs to the log as well as doing synchronous aborts. Now, be aware that because we could crash between phase 1 and phase 2, our recovery methods on our compensator may wind up being executed multiple times simply because we may crash in the middle of a recovery phase, in which case we'll rerun it again. We'll talk about the ramifications of this later on. Here's the object model. You got some transactional object that implements some interfaces that you defined however you want, right? That's in your DLL. It uses the clerk, which it gets simply through a co-create instance call on a well-known class ID. And it uses the ICRM log control interface to write out log records as he does his work. At the end of the transaction, the infrastructure will then go off and create an instance of your compensator class, who implements ICRM compensator, and all of the records you wrote out inside the transaction get delivered to the compensator, right? Both during prepare time and during notify time. That is phase 1 and phase 2. So here's how we use a compensator. It's very simple. My transactional object creates the clerk and says, here's who my compensator is. Here's his class name, right? I typically do this during iObject control activate, although I could postpone it even later if I wanted to. If I want to protect a normally not protected operation, the pattern is I write out a log entry saying I'm about to do this unprotected operation. And then once I've written the log entries, I then try to do it. And depending on the nature of the operation, I may need to write out one more log entry saying I just did it. Now, as I write out log entries, they're buffered, which means they're not necessarily written through to disk, which means if we crash, we lose them. So I'm expected, before I do an unprotected operation, to flush all of the log entries out to disk by calling force log. I can also, if it turns out the unprotected operation fails, and I know it fails, I can back out the last log entry I wrote by calling forget log entry. And I can do that exactly once to unwind exactly one log entry. Now, the log entries are just blobs. If I'm programming in the C or Java interfaces, it's literally a blob that is an array of bytes. If I'm programming in the VB-based interface, they're basically variants. So every log record is a variant, and it can have a string, an int, what have you. Here's the interface that the clerk implements. I'm not going to belabor this one, but notice that we have a register compensator method through which I can say, here's who my compensator is. We also have a write log record, which is for C++ programmers, and a write log record variant, which is for VB programmers. Here's the code in VB. How else? So notice that this is a component that's going to use a compensator. So I'm going to do some unprotected operation, and I want the compensator to handle it for me, to deal with the cleanup for me. So notice that in my activate call, my iObject control activate, I create an instance of the clerk using a well-known class ID, and I go off and I call the register compensator method saying, here's the prog ID, which is like a class ID, of the component which will be my compensator. And that's it. I'm now set to go. And when the transaction is over, my compensator will be created, and his methods will be invoked automatically. Inside one of my methods, in this case my method called method, notice that I go off, and before I do anything, I go off and I write a log record using the clerk that I acquired at activate time. An intent record we'll assume is just something I set up earlier on that says that's the data that I'm going to put in the log. We'll look at that in detail later on. Right? I write the log record, but because that's cached, I force it through to disk by calling force log. Now I know, no matter what happens, the fact that I'm about to try this operation is out on disk, and I'll be able to detect that after a crash. I then try to do the unprotected operation, and we're done. If for some reason that operation threw an error, notice I'm using the clerk to synchronously abort the transaction right away, right? And I do that in the error handler down at the bottom of this function. Okay, that's how we do it. We create the clerk at activation time, we write log records, and then do work. The compensator, second half of this equation, let's go take a look at that now. Compensator is going to be created by the infrastructure during the two-phase commit, and he's going to be delivered all of the log records that I wrote out inside of my object during the prepare phase. So inside the transaction, my component writes out log records. These will be delivered to the compensator during phase 1, right? The compensator can elect to forget them or let them stay in the log for phase 2. And at the end of this delivery cycle, the compensator is going to be asked the question, are you happy or not? And if he's unhappy, we abort the transaction because he couldn't prepare. If he's happy, then his vote is yes, and provided everyone else is happy too, transaction commits. Now, at phase 2, the compensator will be delivered all of the log records that we kept around in the log or any new ones that we put in during phase 1. And it's at this point that the compensator is expected to issue the offsetting compensating transaction or clean up any resources we may have acquired, what have you. And again, because we can crash between phase 2 and phase 1, and that's a normal, reasonable thing to have happen, we may actually see two different instances of our compensator. One that's used during phase 1, we experience a crash. A different instance will be used during phase 2. So we use the log to keep state between phase 1 and phase 2 to verify that we can survive this crash. Here's the interface that C++ and Java programmers use to implement a compensator. Here's the one that VB programmers implement. And they both are identical except for the data types. So we'll look at this one since this is what more of you are likely to do than the previous one. Except for the first method, notice we have 3 groups of 3 methods, right? A prepare group, a commit group, and an abort group. The prepare group of methods is used during phase 1 of the transaction. And so the scenario is, we deactivate the root object, we try to commit the transaction. The compensator gets a begin prepare variance, followed by one call to prepare record variance for each log record that we've written out during the transaction. Once we've been delivered all of these records, we then get delivered an end prepare variance, and notice that this one returns a Boolean indicating whether or not we're happy. If we return false from this thing, the transaction aborts. If we return true, transaction can commit provided everybody else is happy. That's phase 1. During phase 2, the notify phase, one of those 2 groups of methods will be called, depending on the actual outcome of the transaction. In the case of a successful transaction, we'll get the commit sequence called, very similarly to the way they were called during prepare. If the transaction tanks and aborts, we'll get the abort sequence. The really important thing to note here is that the end functions of commit and abort don't have a variant, a bool. They don't have a Boolean result. Because at this point, the transaction outcome has already been determined. It's too late to change your mind. At this point, the best you can do is issue a compensating transaction to somehow undo the work you did earlier on. We talked more or less about how we write out log records. Let's just summarize it right here. So we write out records out into the log, and they're either structured or unstructured. If we're using the lower level C++ style interfaces, they're literally blobs, which is just a variable array of bytes. The format is totally application sensitive. You define what's in them, that's what goes in there. If we're using structured log records, which we definitely are if we're working in VB, then each log record is simply a variant, right? So when we write out a log record, we give it a collection of variants as a VB-style collection. And each one of these variants will be written out to the log, and these will be delivered to us later on. If we wrote out blobs, then the compensator is expected to implement the blob-based interface ICRM compensator. If we wrote out variants, the compensator is expected to implement the one that we looked at in a bit more detail, which was ICRM compensator variants. And this slide indicates correctly that we can't mix the 2 kinds of records inside a single transaction. Here's an example of some VB code that writes out log records during the transaction and then consumes them at prepare time. So the top code fragment would be something that you would see in a normal transactional object. So to build a log record, we basically make a new VB collection, start adding variants of whatever data type we want into that collection, and then we call write log record variants. And he enumerates that collection, writing out a log record for each variant in the collection. That's what we do inside the transaction. Inside the compensator, we simply implemented ICRM compensator variants. And for each record that got written out, this method that we're looking at the bottom of the slide will be invoked given the variant that was stored out in the log. Right? And notice that in this case, I'm simply reconstructing the previous balance and new balance from the log. Right? If you look at the top frag, right, we write out the previous balance, then the new balance. Well, in this compensator, what I'm doing is just keeping track of where I'm at. First time you call me, I say, aha, that log record is the previous balance, I'll cache that. Second one is the new balance, I'll cache that. Right? We then go off and do something with, decide whether we can prepare or not, what have you. And we return true or false depending on whether or not we can prepare. Now, you'll notice I use a rather unorthodox syntax at the bottom of this slide. Technically, you cannot use the return statement in Visual Basic, but in PowerPoint, it's very, very forgiving and allows a hybrid of C++, Java, and Visual Basic syntax all in the same code fragment. So recovery. I mentioned a couple of times that we can crash between phase 1 and phase 2. And so when that happens, we need to do cleanup, right? We need to be able to deal with the fact that we may have said yes to some committed transactions and we need to finish the work. Maybe it turns out a transaction tanked somewhere downstream, and we need to do the cleanup. So marking a server application as CRM aware means that when the process starts up, the system managed recovery log is going to be interrogated, and for every log record that's still in there, we're going to run the phase 2 notifications to allow all of the compensators to do the cleanup. Now, there's some interesting issues here. For one thing, this may block the CRM infrastructure from working. If there's a lot of recovery records that need to be processed when the process starts up, when I go off and try to reacquire a clerk to go do some more compensation work, I'm going to get back a well-known H result telling me that we're doing our recovery and that I should try again later, right? Additionally, if we crash during the recovery phase, we're going to start that process up and do it all over again and run the recovery all over again, which means it's possible that some of my recovery operations may run more than once. And this is really going to affect the way I write my compensators. So, well, this slide says everything I just slide. Let's just cut to the bottom bullet. Actions that we do in our compensators, that is our phase 2 handlers, have to deal with idempotency. And what is idempotency? Idempotency says doing it many times is the same as doing it once. Right? So something like setting a variable to x is idempotent. I can set it to x once. I can set it to x 1,000 times. It still sets it to x. Something like the plus equals operator in C++ or Java is something that's not idempotent. That is, adding 5 to a number multiple times is not like adding 5 to a number once. And because the recovery phases can run multiple times, it's critical that our phase 2 work that we do in our compensators is written to be idempotent. That is, that we only do idempotent operations. And that's all this slide is saying, right? If we don't, we run the risk of reissuing a compensating transaction too many times, and this would be a bad thing. Now, CRMs are kind of seductive because they give you a lot of the benefits of resource managers. They allow you to build your own transactional resources. So this brings up an interesting question. Can we expect SQL Server 8.0 to be written using the CRM infrastructure? The answer is a definite no. There's some things that the CRM plumbing don't give to us that resource managers do give to us. One of the most important things we don't get from CRMs is isolation. There is absolutely no support for doing concurrency management with CRMs. We assume that the things that you're operating on are already isolated and are not going to be used by multiple transactions. If they are, we have a lot of work to do with our compensators to deal with this, right? But the general assumption is that's not going to happen. Additionally, the CRM infrastructure isn't going to do all of the internal atomicity or consistency. We can't put constraints on tables in a CRM. We can't ensure that everything happens atomically. If it's our job to basically build in all of these ACID properties, it's simply a simpler way to do it, right? So the CRM infrastructure is good for protecting certain kinds of operations against transactional style problems, but in general, they're not going to replace, your databases and queues. They're just another, thing that we have in our bag of transactional tricks that we can play to build, really effective transactions and really good transactions. Okay, let's stop talking about transactions for a few minutes. I'm tired of it. I don't know about you. Let's talk about something else. Remember the 3 principles that we talked about early on, right? One principle was put the application code on server machines, not on client machines. We've talked a lot about that. Second principle was transactions are the way we do things. I just talked a whole lot, probably too long about that for your taste. Let's talk about the third principle, which was, while we build things using COM components, these COM components use a variety of communication protocols to get their work done. So what we've been talking about so far kind of implies a very simple model where we invoke methods by making DCOM calls. The methods either invoke other DCOM methods on downstream objects, or they make data access calls to SQL Server or Oracle or what have you. So we've really talked about two kinds of communication protocols, DCOM and generic data access protocols like TDS or whatever Oracle uses. Now, these things are great for doing communication within a single transaction. Some reasons are the transaction flows with the context. So we have this really nice composition because of the way context properties flow. Also, the transaction time we want to be in the millisecond range, not in the hours or even minutes range. And what this means is we need the fastest possible communication protocol possible. And to be frank, DCOM is fairly efficient at doing communications, as are most data access protocols. Additionally, if we think about inside of a transaction, it's all happening on the server boxes. It's never happening on the client boxes. The clients initiate it, and they see the results, but they're not running the transaction themselves. So the associations that we have, that is the machine-to-machine associations, tend to be fairly static because we have a static number of server machines over any given period of time. And this makes it very possible and reasonable to pool expensive connections, like database connections. Additionally, the whole plumbing of the way DCOM and data access protocols work, especially with OADB, is built to reduce memory-to-memory copying. So if I'm moving a lot of data back and forth, the architecture is designed to do it in as reasonable a way as possible and still be generic. So we get very, very good performance if we use DCOM. We get very, very good performance if we use data access protocols. And for within a transaction, it's basically the way we do everything. Turns out, though, that there are scenarios where these two protocols fall down. Both of these two protocols, data access protocols and DCOM, tend to be connection-oriented, which means the sender establishes a connection, holds that connection, starts sending requests, and all of his requests get pinned to a particular server machine. And this gives us way fewer opportunities to do load balancing or migration of context than we would if we didn't establish connections, right? An ideal world would be we'd live in a completely connectionless world. And every request would just be dispatched to some anonymous pool of servers. One of them would pick it up. And each time we had a request, it would be picked up by a different server box, right? This is the optimal case in terms of load balancing, right? Because we don't want to be pinning ourselves to a particular server machine because it inhibits our opportunity to smear the load across multiple hosts. Now, connectionless protocols make this possible, and there's a couple of connectionless protocols we have at our disposal. One of them is called HTTP, which is the one we use on the web. Another of them is called MSMQ. Both of these give us a lot more flexibility in terms of load balancing than we get with DCOM or data access protocols. There's some other problems we might want to think about. One of them is that both DCOM, data access protocols, and MSMQ have difficulty penetrating firewalls. Firewalls, as you know, are the piece of software that the system administrator puts between you and what you want to do. And while there's a few innovations in COM for Windows 2000 that make firewalls a little bit easier to penetrate, in general, they're always in the way. And it turns out that HTTP is the easiest way to pierce through a firewall. And if we want to build applications that work across the internet, this is pretty much a fact of life. So kind of the conclusion of this little discussion is HTTP is the de facto protocol we use when clients access our server-side objects. Doesn't mean it's the only one, but it's the de facto one. It's the universal one that we know will always work. Now, if we're going to talk HTTP to our COM+ server applications, those HTTP requests have to go somewhere, and in the world of COM+, the place they go is this product called IIS, or Internet Information Server. And IIS supports two techniques for invoking methods on server-side COM+ components. One of them is fairly new. And this is sometimes called COM Internet Services. Sometimes it's called tunneling TCP. And the idea here is IIS allows the client-side runtime to establish a connection through an HTTP request that will do port 80-based communications, which is what many firewalls use to detect whether we can get through or not. However, once we establish the first request, It's just straight DCOM calls. The only difference is we're using port 80 instead of the random port numbers that DCOM likes to use. This is a reasonable technology, but to be frank, it's only a matter of time before more firewalls start blocking these things, which means, it's not necessarily the way that we can always pierce firewalls. The much more accepted way of doing this has been around for a little bit longer as well. And this is to basically use ISAPI extensions or to use active server pages to invoke methods by sending straight HTTP and straight HTML, both from the client to the server and from the server back to the client, right? IIS is very happy to do this. It's been happy to do this since NT4. And the idea is that we just use scripts, which we call active server pages, to invoke the actual methods on behalf of the client. The request and the response messages are presented to the scripts, and through extended context, the HTTP request and response are also exposed to our underlying objects. This picture shows pretty much the way a COM+ application works. Client uses a web browser or something more exotic on his machine to talk HTTP to the IIS daemon on one or more server boxes. The IIS daemon then makes DCOM calls to COM+ configured components that go off and make data access calls, and that's the way we do it, right? Very, very simple. Notice that there are 3 protocols involved, but only one between the client and the object. Can we talk DCOM from the client to the object? Sure. But again, that assumes that we don't have firewall problems. And it also assumes, a somewhat different programming model, right? And to be frank, using HTTP to do this stuff is a very, very sane way to go and has lots of positive benefits and, is the way I would recommend trying it first. And only if it doesn't work out the way you like should you start using DCOM from the client to the server. So we saw how the client gets to the server, and we've seen how the server does its internal communications. However, if we look at DCOM and HTTP and to a somewhat lesser degree data access protocols, all of these things are just glorified RPC protocols. And the idea is the client sends a request, the server processes the request and sends back a response, and the client is blocked while the server is doing his work. The programming abstraction of DCOM and even of HTTP is very, very low, very, very close to the wire, very low level, and very, very often too close. More often than not, we would like to program at a higher layer of abstraction, right? And this just turns out to have tons of benefits. Another problem with RPC-style communication is it tends to rely on synchronous communication and direct communication. And these both have tremendous downsides. So let's look at one last protocol, and then we'll call it a day. MSMQ. MSMQ is an infrastructure based on explicit message passing. And message passing has been a very long-running alternative to RPC-style communications and has lots and lots of benefits over RPC. Right? The downside is it's typically not as fast in terms of raw execution speed, but the benefits we get for using it are pretty tremendous, as we'll see. The idea when we use MSMQ is that we're building communications into the application. That is, we're being deliberate. Rather than trying to say, oh, we're just making method calls and it's magically being remoted, we're saying, no. There's a message, and I'm going to send it, and you're going to receive it, and we're going to both talk about the message. Right? We're going to put it on the kitchen table and talk about it, not like Uncle George up in the closet who we don't really want to say anything about. The message is a living, breathing thing in this programming model. Now, messaging is good, but it turns out that MSMQ gives us something beyond messaging, which is queuing. And the idea behind queuing is, rather than talking directly to the server process who I'm trying to get this message to, I go through a queue. And this queue gives me time independence. It means the server doesn't need to be available or running at the moment I send the message, right? And I don't have to remain running once he decides to go off and harvest the message off of the queue. And MSMQ is a very, very simple to use technology for doing queued message-based communications. And to be frank, it's the most underutilized aspect of this whole Windows DNA story. And people who use it are very, very happy. Now, here are some reasons you might want to consider using MSMQ. It gives us a very reasonable way to do prioritization of calls or requests, right, which was very, very hard to do in HTTP and in DCOM. It gives us deadline-based delivery and flow control, which allows us to keep from saturating the network or the system with too much work. We can simulate RPC-style invocation very, very easily using MSMQ with a variety of infrastructure facilities that are provided by the system. And we also get a routing infrastructure that does store and forward style communications that allows me to do disconnected operation. Additionally, it's very, very easy to build load balancing using MSMQ. Programming model for MSMQ is dirt simple. there are two programming abstractions. A queue, which is simply a named ordered repository of messages on some host machine, and it's named by a GUID. A message is simply an opaque array of bytes that has certain MSMQ-controlled headers, and those are the things we deliver to the queues. And MSMQ handles all of the underlying message delivery, acknowledgments, and all of the plumbing that we need to worry about. All we have to do is say, I've got messages in queues, and it's a very, very direct model. So this slide shows you the basic communication paradigm, which is the sender has a message, he sends it to a queue, and at that point he can go away. At some point later on, the receiver can decide he's ready to do his work, he can go off, harvest the message off of the queue, and then do the work that's represented by this message. There's a lot of ways to program MSMQ. The most common way under NT4 is to use the OLE automation style interface that's on top of the low-level API. And this is what the vast majority of MSMQ programmers do. The first and third options on this slide are fairly esoteric, and not a lot of people use them. COM+ gives us yet another way to do it, called queued components, which allow us to turn a normal DCOM application into a queued application without having to write any code. Here's the object model that the OLE automation interface exposes. This is available both under NT4 and under COM+. There are three types that are important: is the queue info, which we use to name queues, the queue, which is the queue handle, and the message, which is the thing we send. Here's the VB code to go off and open a queue that we already know about and send a message. And notice that we're using the flag at the very last line, MQ under MTS transaction, which says auto enlist. If I'm a transactional component, this message transmission should be a protected operation. And if the transaction aborts, the message never happened. Here's the code for receiving a message in VB. And again, notice towards the bottom, we're also using the flag MQ-MTS transaction, which says implicit transactioning. Look in my context, and if I have a transaction, do this receive in the context of a transaction. Which means, if the transaction aborts, I never receive the message and put it back in the queue. Under MSMQ, only one party is ever going to receive any message in the network. So that I can have many people reading messages off of a single queue, only one of them is going to pick up any particular message, right? So receives are destructive. And once I receive the message, if it's inside of a transaction and the transaction aborts, to ensure that the work that was represented by this message actually gets carried out, the message gets put back into the queue so someone else can get it. We talked a little bit about transactions. Oh, I've basically told you everything you need to know about transactions. The send happens inside the scope of a transaction, so in essence, the send never happens if the transaction aborts. One other ramification of this is the message doesn't really exist until the outside of the transaction, until the transaction commits. So if I do a send inside of the transaction, no one's going to be able to receive that message until the transaction successfully commits. This implies that a message in an MQ system has two transactions associated with it. The one that writes it, or the one that sends it, and the one that reads it, or the one that receives it, right? And so very often we build workflow-style, multi-transaction programs using MSMQ as kind of the backbone of things. And again, the receive, if the receive is done inside the scope of a transaction and we abort, the message goes back into the queue to be dispatched later on. Hopefully we will not abort again. And if we do, then we have the poison message problem, which we'll mention in a second. Now, MSMQ is not that hard to use. In fact, it's extremely easy to use. And people are using it a lot today and having really great results with it. Very easy to use from VB. And the interesting thing about MSMQ is we state that we're going to become deliberate about communications, right? That we know we've got messages and queues, and that's the way we build things. Several aspects of building an MSMQ app, though, require you to write a little bit of code. You have to go out and manually create the queues, which is literally one line of VB code, so that shouldn't scare you. You also have to go off and build the dispatching plumbing that sits and listens on the queue, pulls the message off the queue, and starts the work that the message represents. And this can be non-trivial if you work in Visual Basic. It's not too bad to do in C++ or Java. You also have to deal with the poison message, which is the message that every time you receive it causes the transaction to abort. So if we just let it go back into the queue, we have an infinite loop. Right? Dealing with poison message handling, although there are well-known techniques, you get to implement them in normal MSMQ programs. Finally, marshaling the content of the message, the body. That's something you have to do, which is extremely trivial to do, especially in VB. So some of these problems, in particular the server-side request dispatching, is going to be addressed in MSMQ itself. So MSMQ under Windows 2000 will ship with a trigger infrastructure, which allows us to attach operations to queues so that when the message arrives, something happens. But all of these problems and a few others are addressed if we use COM+ queued components. And the idea behind COM+ queued components is it's checkbox programming, right? Rather than writing explicit code, I take a normal DCOM style object model and I start turning on the queued access checkbox, which simply says, I would like this thing to be accessible via both queued invocation and normal DCOM style invocation. And what happens when I do this is the following. When a client creates the object, rather than getting a proxy, a normal DCOM proxy, he gets something called the queued component recorder, which simply sits there buffering every method invocation you perform on it and building a buffer with all of these parameters that you're sending. Right? Nothing happens except we record them. When the recorder is released, it sends a single MSMQ message containing all of that information to the server-side machine. Right? And the recorder is transactional, so that can be composed inside of a transaction. On the server side, there's another component called the queued component listener that's sitting there waiting for messages on the well-known queue names. And when a message arrives, he creates the queued component player, which then creates an instance of your actual component and plays back all of the method invocations that were performed by the client. And the transaction outcome is going to be tied to the message reception. So if my transactional component, which gets created by the player, decides to set abort or somehow the transaction winds up being aborted, the message basically goes back into the queue, except it gets put into the poison message handling infrastructure of the queued component system, so that I don't have to worry about having these poisonous messages that just constantly cause aborts. They'll get retried a few number of times, but not infinitely, just clogging up resources in my server. The benefits of using queued components are pretty simple, right? It's transparent. I don't write my own code. It just happens. I click a checkbox, and the next thing I know, I've got MSMQ access. Poison message handling is built into the plumbing. I don't have to do any marshalling by hand. Probably the most interesting aspect of this is that the security plumbing gets screwed around with by the queued component listener and player, such that all of my role-based security will now work based on the client's ID, which is very, very hard to do in raw MSMQ. Right? And again, the idea is queued components are just transparent use of MSMQ. So to wrap up, 3 principles. Run the code on server machines, not on client machines. We do transactional programming, and we use these various protocols to do component-to-component communications. Right? The whole thing is glued together using COM+, and the central aspect of the COM+ programming model is context. Right? That's the deal. I have nothing else to say about COM+. If you got all that stuff, you guys are ready to go out there and build COM+ applications. Courses you might want to look at. The Microsoft Systems Journal issue of May 1999 has several very detailed descriptions of the context architecture, as well as a laundry list of the new services. The rest of these resources are also very, very useful for getting up to speed on COM+. Thanks.